We're going to jump around on topics a lot. I might start off on completely factored polynomial 2x to the fourth plus 2x cubed minus 12x squared
Hold on.
minus
You're breaking up the audio. I'm having a hard time understanding you. 2x to the fourth plus what?
6x cubed minus 12x squared minus 16x.
That's it?
Yeah.
Okay. And we're supposed to factor that?
Yeah.
Well, the first thing to do whenever you're asked to factor something is there a greatest common factor that I can remove?
Yeah.
What is it?
Correct.
Uh-huh. And what is left?
X cubed plus 3x squared minus 6x minus 8.
Okay. Now we are faced with a cubic. And there's only two ways to solve a cubic. One is by grouping if the coefficient ratio is the same in both cases, but notice it's not. In other words, 1 is to 3 is not the same as 6 is to 8. So I can't factor it by grouping, which leaves two other methods. One is a calculator, and the other is the rational factor theorem. I'm going to guess here that they want you to use the rational factor theorem.
Yeah.
Okay. What are our possible rational factors? Let's list them.
Oh, plus or minus 1, plus or minus 2, plus or minus 4, and then plus or minus 8.
Have you had upper and lower bound theory yet?
I'm not sure.
Okay, doesn't really matter. Okay, so our next goal is to see if any of these are a solution to this cubic. And if any of them are, then we'll be able to reduce that cubic to that linear solution and a quadratic, and then we can handle the quadratic quite easily. So the goal from this point would be to find, remember the rational factor theorem says that if there is a rational factor to this cubic, then it's one of these 8 numbers, plus or minus 1, plus or minus 2, so forth. So the first thing we want to do is find out what is the rational factor. Well, the way I always do it is I always do the stuff that's the easiest arithmetic. Let's start with 1. And let's do synthetic division, because if we find a factor, we will have the quadratic available. In other words, what comes out down here is the resultant quadratic if this is a solution. So synthetically divide that for me. Tell me what to write in each spot here.
You put the 1 down, and then 1 times 1 is 1. And then 4 times 1 is 4 minus 2. And then negative 2 is negative 10, so it doesn't work.
Okay. This has to be 0 for it to work. Let's try minus 1. The next easiest thing. Now, if you've had upper and lower bound theory, there might be a better place to start, and it would be with the bigger number. In fact, let's do that, just so we can experiment a little bit with it. Let's try 8, and I'll show you why. I know now that you know how to do synthetic division, so I won't force you to do that. Big plus. The fact that the sign on the result is the same on every term, in other words, it's a plus there, a plus there, a plus there, and a plus there, tells me that plus 8 is an upper bound. Well, we kind of knew that, but that's upper bound theory. If these signs alternated, then it would be a lower bound. And in fact, we can probably prove that quite easily. Let's try minus 8 and see what we get. 1 minus 8 minus 5, 40, 34, big negative, big negative. Well, that's plus, minus, plus, minus. That tells us that minus 8 is a lower bound. So we know that plus 8 is an upper bound. That whatever solution there is, it's going to be smaller than plus 8. And minus 8 is a lower bound. So the reason that's useful is we don't actually have to try every single number here. In other words, if we discover that plus 2 is an upper bound, well, then I don't have to try plus 4 or plus 8. So there are a few shortcuts you can take. Let's see if we find anything that is an upper bound. Let's try 2. Well, gives me 1, 2, 5, 10, 4, 8. I found the 0 accidentally. However, you can see that based on upper and lower bound theory, that I would never want to start out there, because that's not going to tell me anything at all. In other words, I already know plus or minus 8 is an upper and lower bound. It's the biggest number there and the smallest number there. So if I start here and I discovered that plus 2 is an upper bound, that would put me 2 steps ahead of everybody else, because everybody else is going to have to check plus 4 and plus 8. I wouldn't have to. But I got lucky that 2 was a solution. So what's the linear factor, and what is the resultant quadratic? In other words, there is a linear factor and a resultant quadratic that that cubic breaks up into. What's the linear factor?
X squared plus 5x plus 4.
That's the quadratic. Linear factor is x minus 2. Because 2 worked. And this is the 0. It's not the linear factor, but if the linear factor were x minus 2, the 0 would be 2. Okay? So whatever number you put in here, the linear factor is always x minus that number. Now, we're not quite done, because x squared plus 5x plus 4 factors into what?
X plus 1, x minus x plus 4.
There's your solution. There are 4 zeros to that quartic. What are they?
0, 2, -1, -4.
Yeah. A lot of people don't pick up that one right there. All right, what else you got tonight?
So I'll have like add and subtract rational expressions.
Okay.
And the first one is 3x over x plus 2 plus x over x minus 2.
What do we have to do in order to add these two fractions?
You need to make the denominator the same.
We need to come up with a common denominator. What's the common denominator, and how do you figure it out when there's variables involved?
The common denominator would be x plus 2 and x minus 2.
The product of the two variables we're looking at is always a common denominator, because the definition of a common denominator is anything that each term divides evenly into. Well, x plus 2 divides into that x minus 2 times, and x minus 2 divides into that x plus 2 times. So that is always going to be a common denominator. It won't always be a least common denominator, but in this case it's the lowest common denominator also. So I can write that over here also. And let's leave it unmultiplied together at the moment. What goes here?
3x, x minus 2.
And here?
X and x plus 2.
Okay, so at this point, we know our answer has x plus 2 times x minus 2 in the bottom. And there is a reason I don't multiply those together. There's a possibility that by the time I figure out what that is, there will be an x plus 2 or an x minus 2, in which case I'll be able to cancel it out. Although it doesn't look like that's what we're going to get. What do we get as a numerator?
3x, x minus 2 plus x plus 2.
Well, we do have to multiply the numerator out. And the reason is that we're going to combine that. In other words, we need to simplify that. Once you found a common denominator, then you act on the numerators. So I need to simplify this numerator. So I need to distribute that, I need to distribute that, and I need to add them all together. So let's start by distributing the left. And I'm going to add to that x squared plus 2x. You with me?
Mm-hmm.
Okay, so we'll simplify this. That's 4x squared minus 4x. And I can factor that. I can take out a 4x, leaving behind x minus 1. And my denominator is still what I started with, x plus 2 times x minus 2. And there's your answer. If you ever have a choice as to whether to leave something factored or multiply it together, I always leave it factored, because it's a better answer. For whatever reason we wanted this, perhaps it's to multiply it by something else, and maybe that something else has one of these factors. So you're always a little bit ahead of the game if you leave it factored, as opposed to multiplying these out and putting quadratics in the numerator and quadratic in the denominator. At least that's my feeling. Your teacher might actually have their own opinion. I don't know. Do you have answers on these?
Yeah, backwards.
should be the answer that they give.
Yeah, they just leave the denominator like that.
Yeah. Oh, and they leave the numerator as 4x squared minus 4x?
No.
Oh,
Your answer.
okay, so they leave both of them factored, the numerator and the denominator. Okay. What else you got?
X over x minus 9.
X squared minus 9?
Yeah.
Okay.
Plus x over x squared minus 5x plus 6.
Minus 5x plus 6?
Yeah.
Okay. So this is going to be a little tougher to find a common denominator. A common denominator would automatically be this times that. But let's examine that for a second. Let's say we had this question here. What is the least common denominator for this problem?
X?
X squared. Remember that whatever the least common denominator is, it has to be divisible by both terms. X would not be evenly divisible by x squared. So it can't be x. But x squared is the answer, because x squared is evenly divisible by x squared, and it's also evenly divisible by x. My point is that we're not always going to just multiply these together and say that the common denominator would be x cubed. We don't always have to do it that inefficiently. In other words, I can tell that x squared is a common denominator. I don't have to go to x cubed to come up with it. Okay? So, that being the case, let's factor each of these and see if we can come up with a common denominator that is not just the product of x squared minus 9 times that, because that's going to be very cumbersome. That would be a quartic. How does x squared minus 9 factor?
X plus 3x minus 3.
How does x squared minus 5x plus 6 factor?
X plus 3, no, x minus 3 plus, x minus 2, x minus 3.
Okay. Now we can begin to see that our least common denominator doesn't need to be a quartic. In other words, what is my lowest common denominator going to be based on what I'm looking at here? It's clearly got to have an x minus 3 in it. Clearly got to have an x plus 3 in it. What else does it have to have in it?
X minus 2.
Yeah. That is my least common denominator. Why? Because that term divides evenly into it, and so does that term. That's what I need. Okay, so what goes here?
2x. Oh wait, just x. Wait, I'm confused. What?
Divide those two terms into these three terms. Take your answer and multiply it by the numerator. That's what goes there.
Oh. X and x minus 2.
Yeah, x squared minus 2x. And I go ahead and multiply them together because I know I'm going to have to simplify it by combining it with whatever I get over here on this numerator. What is this numerator going to be?
X squared plus 3x.
Right. Okay, now combine the numerators and I will write it all as one term.
X squared minus 2x.
Hold on. Let's. How many x squareds do we have in sum?
2x squared.
How many x's do we have in sum?
X.
And they're all over. So that's our answer, unless this happened to produce a linear factor that was the same as one of these that I could cancel. But it doesn't. In other words, I can put this back to the way it was, which is 2x times x plus 1, which is, let's go ahead and write it like that. It's 2x times x plus 1, right?
Yep.
Is that what I had there? I had 2x squared minus x. What am I thinking? 2x squared minus x. I can take an x out only. So I have x times 2x minus 1. If this happened to be the same as one of my bottom linear factors, then I could cancel it. But it's not. I don't have anything the same. So that's my final answer. Now, what's this equal to?
-1.
Uh-huh. And that's the only kind of things that you can cancel without them being identical. In other words, over here on the left, I'm looking for something that's an x minus 3, an x plus 3, or an x minus 2 in the numerator. I didn't find it. But the only time I can do a cancellation, if they're not identical, is when I have that situation, where I have a minus b over b minus a is always equal to -1. So had I come up with, say, 2 minus x, I could have crossed it out with that and replaced it with a -1, or 3 minus x even. What else?
X squared plus 6x plus 9 over x squared minus 4.
Whenever you... Go ahead.
Times x plus 3.
Like this?
No.
The whole thing times x plus 3?
Yeah.
Like that?
Over x minus 2.
Whenever you see quadratics like this in a rational function, always know that the answer lies in factoring. So factor the numerator.
X plus 3.
Factor the denominator.
X plus 2x minus 2.
I tell you why I like to write it this way. Each time you've given it to me, you've given me the plus factor first, and you might say, well, what's the difference? The associative property holds. The difference is when you go to difference of cubes and sum of cubes, it's very helpful to know that that first linear term is the same sign as what you started with. You know what I'm saying? Have you had difference of cubes?
Not really.
Here's what, let me tell you why I feel strongly about this. This is the way I remember difference of squares. You gave it to me as a plus b times a minus b, which is correct. But if you memorize it this way, now the difference of cubes, the first linear term's the same sign. The second quadratic is the opposite sign. And sum of cubes factors also, and you'll be expected to memorize this. The first term is the same sign. The second term is the opposite sign. And now you can see why I like to put this first. Because in all three of these cases, the first linear term is the same sign as the problem that we're trying to factor. And that's the reason I think that the order is significant. It's not incorrect. I would never tell a student that it was incorrect if they factored it into, x plus a plus b times a minus b. But for future math purposes, it might be worth memorizing it the other way. All right, we're going to multiply this thing by x plus 3 over x minus 2. So the first thing we want to do is cancel anywhere that we can. Wow. You sure I got the problem right? You sure that this term is x plus 3 over x minus 2? Because it sure looks like it should be the opposite. It looks like it should be the reciprocal.
That's what it says.
It says x plus 3 over x minus 2?
Yeah.
Could it be division?
No, it's multiply.
Okay, well, that's all right. We'll deal with it. It would be nice and convenient if it was the reciprocal because we could cancel out a lot of things. Whereas we can't cancel out anything here. So this is not only the intermediate step, but it's the final answer. I mean, I suppose you could write it as x plus 3 cubed over x minus 2 squared times x plus 2. I'm not sure if that's necessarily a simplification, but I don't see anything else that I can do. Do you? I mean, there's nothing that can be canceled.
No, that's what the answer key says, what you just said.
Really? Because notice how pretty it would be if this was a typo and it really was this. Then you could cancel that with that, you could cancel that with that, and you'd have x plus 3 over x plus 2 as an answer. And that would be what I would expect whenever I see a problem like this. But if they gave the other answer, then it must not have been a typo. What else?
6x plus 2 over x squared minus 1.
Okay, let's factor top and bottom.
The top is, 2 times 3x plus 1.
Yeah, it doesn't look like it's going to do much good to factor it, but what's the bottom?
Plus 1.
Can't do anything with that. That should be the answer.
Well, I didn't finish saying the problem.
Oh, I'm sorry.
And then times x minus 1 over 3x squared plus x.
3x squared what?
Plus x.
Okay. All right. Now a lot's going to happen. So if I go back factoring that. Factor this. And now cancel. This is a more traditional kind of problem. So now the numerator has 2 in it, and the denominator has x times x plus 1 in it.
Yep.
And it's worth noting, I suppose, that when I draw a line through there, it's not quite right to say I'm canceling it. I'm replacing it with the number 1. I'm not replacing it with 0, notice. In other words, all I'm doing is dividing top and bottom by 3x plus 1. And that's how I get a 1 there and a 1 there. I cancel it and I don't write it because it is 1. But it's worth knowing that it's not 0. I'm not really canceling it. It's not like I've subtracted 3x plus 1 from top and bottom. Okay?
So this is 3 plus 12 over x all over 1 minus 16 over x squared.
Okay? We want to treat these separately. Let's work on the numerator. How do I add those two fractions together?
Find a common denominator.
Okay, which is?
X.
Okay. So
3x over x.
Right?
Mm-hmm.
Do the same thing to the bottom.
X squared over x squared.
Now what can we do? In other words, now we can actually end up with a rational function as our numerator and a rational function as our denominator. So let me write that step because it's worth seeing. Ooh. All right, let me write it first before I get all excited about factoring it. Now let's simplify this. How do I simplify this?
When you do flip the denominator and multiply.
Flip the denominator and multiply. So I've got this times x squared all over. I'm going to factor that while I see it because I see that that's going to cancel out. If I go back and factor this and take a 3 out, then I got 3 times x plus 4. So now I can cancel that with that. I can cancel that with that. So now I have 3x in the numerator, and I have x minus 4 in the denominator. And there's my answer. Now whenever you get a situation, if you take a look at this fraction up here that I'm looking at, if that wasn't x squared, let's say it was x like that, I've got the same denominators. I can just cancel them out like that, leaving 3x plus 12 over x squared minus 16. If I were to have the same numerators, I could not do that. I can only do that if I have the same denominators. In other words, if the denominator of the numerator is the same as the denominator of the denominator, then I can reduce that instantly by just doing that. And that doesn't really save you much, because obviously you would flip this and multiply and realize you could do that instantly anyway. But it's worth knowing that you can do it, and it's worth knowing that you can't do it if the numerators were the same. In other words, if I had something like this all over this, I cannot do this. I'd have to flip it. In other words, the answer is x plus 2 over x minus 1, not x minus 1 over x plus 2. So just a word of warning for that situation. Okay, what else?
3 minus 1 over x plus 3.
3 minus 1 over x plus 3, okay.
All over 3 plus 1 over x plus 3.
Like that?
Yeah.
Okay. Well, x plus 3 will be our common denominator, and we'll be able to cancel it out, so we might as well go that route. I can't see anything else to do. So let's rewrite it. Subtract the top. What do we get?
3x plus 3.
Yeah, we can start there. So what does that simplify? Well, now let's just do it like this. The bottom is plus, right? So what can we do now?
3x plus 9 minus 1.
Well, I prefer to simplify it as quickly as possible. Now let's write what we have left. So we have 3x plus 9 minus 1 all over 3x plus 9 plus 1. And I can't do any more. Okay?
F of x equals x minus 2 over x minus 4. And this is to graph rational functions.
Okay? It's the first thing we want to do when we graph a rational function.
Find the vertical asymptote.
Find the vertical and the horizontal asymptotes. What's the vertical asymptote?
2 and 4.
And the vertical asymptote is just 4. The vertical asymptote is where is the denominator equal to 0. That's the only thing you need to ask for the vertical asymptote. And it's only equal to 0 when x is equal to 4. What's the horizontal asymptote?
1.
Yeah. Now, this is a hyperbolic function, meaning once you have your vertical and horizontal asymptotes in there, we basically form a grid with 4 quadrants. And typically, because it's hyperbolic in nature, it's going to look like this. Okay? Now, it doesn't have to look like this. It could actually look like this. Be in the second and fourth quadrant instead of the first and the third. So, let's figure out which it is. How are we going to figure out whether we're up here or down here?
Well, you can do the line test or figure out what the y-intercept is.
How about if we were to put in a number to the right of 4? Put in x equal 5, and what do you get?
3 over 1, so 3.
Right. So if x is 5, we're up here. That tells us which quadrant we're in. That means we're definitely up there. And the other side of that is down here. Now, that's not quite good enough. That's the accurate picture, but the only thing I haven't really decided is where that point comes and where this point comes. In other words, I've got an x-intercept and a y-intercept that I want to tell whoever I'm graphing this for what they are. So how do I figure out the y-intercept?
We set the x equal to 0.
So that becomes 1/2. So I know that the thing has to cross the y-axis right there at 1/2. And the x-intercept is what?
2.
So it has to cross the x-axis right there. So now I can more accurately draw my hyperbolic function. And there is every key point that you need. I have the x-intercepts, I have the y-intercepts, and I have the horizontal and vertical asymptotes. And I have the end behavior correct. In other words, if it's easy to be in the wrong quadrants here. I've assumed first and third quadrants before and found out that it's actually these two. So that end behavior test, which is what you did when you substituted x equal 5, was we were merely going to the right of that asymptote so we could figure out whether we're in this quadrant or this quadrant. And we found out we were in that quadrant. What else?
X squared plus 2x minus 8 all over x minus 3.
Let's factor it just because it's a quadratic that can be factored. In other words, these problems always need you to factor these. I'm not sure I've ever seen a quadratic that didn't need factoring in a problem like this. Okay, let's graph this right here. First step,
vertical asymptote,
which is where?
3.
It's the horizontal asymptote.
There is none, but there's a slant asymptote.
Yeah, there's an oblique asymptote. Whenever you have the highest degree in the numerator is exactly 1 greater than the highest degree in the denominator, you have a oblique asymptote. And it's a linear oblique asymptote, meaning it's a straight line. How do I figure out what it is? I actually do the division. And what do you know? I finally found a case where you didn't want to factor the numerator. Because I have to do the long division. You know how to divide that?
No, but couldn't you just use synthesis?
Well, yeah, but you can use long division just as easy. I'm just illustrating a point here that the only thing that matters is that first linear term that you get. Let's see, 2x minus a minus 3x gives you 5x minus 8, and then x goes into 5x plus 5 times, and then you multiply it back, you get 5x minus 15. You get a remainder of 7, but this is the equation of the oblique asymptote. In other words, whenever you take that, whatever your numerator is that's 1 degree higher than the denominator and you divide it, you always get a linear factor by definition. In other words, if this is x cubed and this is x squared, you're still going to get a linear answer. And you can throw away the remainder. That we don't care about that. What we care about is that x plus 5 is the equation of the oblique asymptote. Well, this was at what, 3? So 5 would be about here. It's got a slope of 1. Let me erase everything. So there's our oblique asymptote and our vertical asymptote. And the function is still hyperbolic in nature. In other words, I expect it to look something like this, or possibly in the other 2 quadrants. In other words, like this. You see the difference?
Mm-hmm.
Okay, so let's figure out which one. So all I have to do is plug in a number greater than 3 and figure out whether I'm up there or down there.
Still.
Well, now it actually would have been helpful to have that thing factored. So let's put it back in factored form. And if I put in a number 4, what do I get? I get 8 times 2 over 1. So I get 16 when x is 4. Well, does that put it up here? I think it does. And if that one is in that quadrant, then this one is down here. And remember, this is the y-axis over here. Okay, so we've analyzed the end behavior, basically, by plugging in a number there, and realized that we got the general picture correct, but we still don't have the specifics. In other words, I don't have the x-intercept and I don't have the y-intercept. Oh, man. What was it? X plus 4 times x minus 2 all over x minus 3, correct?
Mm-hmm.
What is my y-intercept?
Your y-intercept is 2 over 3. No, it's not. 8 over 3.
Okay. Which is, we'll just leave it as 8/3. So this point right here is 8/3 on the y-axis. What's my x-intercept?
Three.
There's actually 2 x-intercepts.
Yeah.
In other words, whenever you set y equal to 0, like that, the only way a rational function is equal to 0 is if its numerator is equal to 0. Doesn't matter what its denominator is. The numerator has to be 0 for this whole thing to be 0. Well, the numerator is 0 at -4 and at +2. And if we look at our graph, we can see that we have 2 x-intercepts. There's one there and there's one over there. That one's clearly at -4 and this one's at 2. So that's a pretty good depiction of our function. You'll notice that there would still be a question that I would have a lot of difficulty answering. Not this one. What's the domain? On this function. Just look at the graph and tell me what the domain is.
-infinity to 3, parentheses, and 3 to infinity.
The tough part is the range. And the range, you need a calculator or some program. In other words, there's no easy way to figure out what that value is on the y-axis or what that value is on the y-axis. And you can see that there's a healthy amount in between that is not in our range. So if I wanted to tell you what the range is, I couldn't do it from looking at the graph. I would have to go in and put this function into my calculator and find what that maximum was, what that local maximum is, and what this local minimum is, and then I would be able to tell you the range. So that's one of the things about oblique asymptotes, is you end up with a difficult range to figure out. Now, one other thing about oblique asymptotes, horizontal and vertical asymptotes. The function can never cross a vertical asymptote, because that would mean you'd be dividing by 0. But functions can cross a horizontal asymptote and a oblique asymptote. In other words, it's not impossible for this thing to look like this. Cross the asymptote and then approach it. Or if you had, say, a horizontal asymptote, let's say you have a vertical and a horizontal, you can have a function do something like this. Cross the horizontal asymptote and then come back and approach it. Whereas on the other side, it might not cross it. It might be like that. So you can cross horizontal asymptotes, you can cross oblique asymptotes. You cannot cross vertical asymptotes. Got 2 minutes. Do you have any? Unfortunately, I have an 8 o'clock that I have to get to. But if you have any last questions that we can answer quickly?
No, I don't.
Okay. Well, sounds like a good place to stop then.
Alright, thank you.
You're welcome, Mina. I'll talk to you next time. Bye-bye.